Hi guys, this is going to be the lecture video for section 2.2 part A. Let me go ahead and get straight to the sharing of my screen so we can get started. All right, let's have that come on. There we go. Sorry for the delay. Okay, so today for section 2.2, we're going to continue talking about set theory, but this time we're going to put it into the context of how we teach the use of whole numbers. Basically, this helps you to understand where the concepts come from of understanding things like how do we make the determination of when we're talking about a number as its quantity versus we're talking about a number as its symbolic representation, whether we're talking about a number that helps us to organize things in order, and also how you would introduce the concepts of more than, less than, and equal to your students, okay? So we're gonna start by this introductory activity. You guys remember this from a couple of lectures ago, where some children are shown these three blocks and they're asked to go ahead and count them, right? And remember, we talked about child one who was able to count them this way, and they would say 1, 2, and 3. And in essence, we discussed that the reason why this child, and again, we're talking about young children, probably starting kindergarten or preschool, the reason why this child might make this mistake is because they have not yet learned the concept of one-to-one correspondence, which, as you know, as we've discussed in set theory, explains how we get equivalent sets, or how we determine that each of the sets we're discussing contain the same number of elements, which is the definition of an equivalent set, that they have the exact same number of elements, even if the elements for each set are unique unto themselves, right? Okay, so obviously child number one doesn't have that understanding, and that's why they're not counting our colorful blocks in the correct manner. Now, child two, if you recall, started a little more strongly. They count 1, they count 2, and then they stop, as if the third block is not there. And again, this is a lack of understanding of the concept of one-to-one correspondence, which is why it's so important to start with that when we discuss set theory, and also just to start with that concept as you start to teach your students. All right, then of course we got to the child that did have the concept of one-to-one correspondence, and they were able to successfully count the blocks as 1, 2, and 3. However, when this self-same child gets asked, okay, so how can you show us 3 blocks? They go ahead and they point just at the last block where they counted the number 3. This is showing a different conceptual misunderstanding. The child understands the concept of one-to-one correspondence. They're corresponding the numbers they have learned to chant, 1, 2, and 3, to each of the individual blocks before them, but they don't understand the idea that the numbers that they're discussing can also make reference to a total quantity. So that's why they say, you tell them, okay, so show me how many are 3 blocks, and they point to the block where they said 3, okay? The next child gets the same exercise, and they successfully have, this would be child number 4, they successfully have the concept, they have mastered the concept of one-to-one correspondence. And when you ask them how many blocks, they tell you there are 3 blocks, and then you say, okay, so show me 3 blocks, what are 3 blocks? They successfully tell you all 3 of them, and they point to the whole group and say, this is 3 blocks. This child has mastered one of the concepts we're going to discuss in today's lecture, which is called the idea of cardinal numbers. In other words, they understand that these numbers, 1, 2, and 3, are not just some numbers they chant to a little song, but rather they represent a quantity. Okay? Now, moving on from that, another thing that has to be explained, okay, when you get ready to teach your students the concept of greater than and less than, before you can teach them the concept of greater than and less than, you have to make sure that they have successfully mastered both one-to-one correspondence and the concept of cardinal numbers, i.e., that numbers represent a quantity. Otherwise, teaching them that one of these quantities is more than the other, or greater than or less than, is going to be out the window. They will successfully understand the concept of equal because they understand one-to-one correspondence. But if you have not also made sure that cardinal numbers are understood, then they're not going to successfully understand how to determine which of these groups of hats has more hats or less hats. And that is one of the things that we're going to discuss today as we discuss a couple of concepts about whole numbers that we can explain with the paradigm that we've been using of set theory. Okay, so let's go ahead and get into our notes. So these are the notes for section 2.2, part A, whole numbers and numeration. Now, excuse me. Numbers and numerals, okay, are basically whole numbers in set W, i.e. the numbers we use for counting, okay? Whole numbers or numerals are what we talk about as the numbers we mean for counting. But like our introductory example, there's a couple things we have to clarify. When we use the word number, we are defining that number as what? We are defining it as an idea of an abstraction that represents a quantity, okay? We can also talk about what do we mean by a whole number. So like if I say 3, I could be using 3 as a number where I'm defining that as an idea or an abstraction that represents a quantity. Or I could be using the number 3 as a numeral where I'm using it to represent the symbol that we see when we write the number 3. So when I write the number 3, depending on how I'm using it, I'm either using it as a number saying I'm talking about the quantity of 3 things, like 3 dots, or I'm using it as a numeral, as in here is the symbol that represents 3. Okay, so it's important to know whether you're using it as a number or as a numeral. Okay, finally, once we make that distinction, here's a couple of ways that we can use whole numbers. We can use whole numbers as cardinal numbers, which is what we were discussing in the introduction. A cardinal number is defined as a whole number that is used to describe how many elements there are in a finite set. In other words, cardinal numbers tell us a quantity. So if we look here at our example, we have set A. Set A contains the set of A, B, C, D. And set B contains the numbers 1, 2, 3, 4. We can see here that they have one-to-one correspondence. Okay, so they are equivalent sets. They contain the same number of elements in each set. And we can see that set A has a total of 4 elements. It has elements A, B, C, and D. 4 elements. In this case, the number 4 right here is being used as a cardinal number. It is being used as a number to describe how many elements there are in a set. Okay, now we can also use numbers as ordinal numbers. And ordinal numbers you're probably extremely familiar with because ordinal numbers are what tell us what order things are in, okay? In English, we have order words, ordinal words where we say something happened first, second, last, then, and then finally. In math, we have ordinal numbers, which help us to determine the order of something. So ordinal numbers are defined as the whole numbers that we use to describe the order. So here in our example, we have set A. Set A, once again, contains the elements of A, B, C, and D. But this time, okay, we want to specifically talk about element C. And element C, as we look at this set from left to right, is the 3rd element in the list. So when we use 3rd, that is an ordinal number. It is telling us in the order in which the elements of our set have occurred, okay? Finally, and this goes with what we talk about as we use numbers all the time to organize our life. We have what's called identification numbers, okay? Identification numbers are symbolic. These are numbers that we use, and here's the definition. It's when we use whole numbers in sequences to name things or as symbols instead of their actual value. And the best examples we have here is we use numbers to identify phone numbers, account numbers, social security numbers. These numbers do not hold an inherent value. They're not defining a particular quantity. It is their actual order or sequence that makes them valuable because that's what gives us an identification of what we're talking about. Okay, so now that you know the three different ways that we can commonly use whole numbers, and we've made a distinction between what is a number and what is a numeral, let's talk about the child that we talked about in our introduction. Okay, the child in our introduction knew how to count from 1 to 3 and could correctly identify that there were 3 blocks and they were able to have that 1-to-1 correspondence, but did not correctly identify what were 3 blocks. They only pointed to that last block where they had named the number 3 because they didn't have a clear understanding of the concept of cardinal numbers. That cardinal numbers, or as we refer to them at the beginning, the numeral, right? The number rather, instead of the numeral. Cardinal numbers talk about the quantity, okay? So if you see here, you can have sets that contain the same quantities, and therefore between them they are equivalent because they will have 1-to-1 correspondence. They will each have the same number of elements, and therefore we understand that regardless what the elements are for each set, each of these sets has a quantity of 3 elements. Therefore, that is the cardinal number we're using. And you can see that here in this example. Okay, we have set A that has a circle, a square, and a triangle. We have set B that have the alphabet letters lowercase a, b, and c. And we have set C that have the symbols for infinity and average and beta. Okay, and despite the fact that each of these sets contains a vastly different and unique elements in them, they all have 1-to-1 correspondence between them. And you can see that right here. Okay, they all have 1-to-1 correspondence. Each of them has 3 elements within their sets. So that is why we can say that sets A, B, and C are equivalent to each other. Remember, that's what that little tilde means, equivalent. Okay, and therefore the quantity of elements inside of each of these sets is 3, and this is where we're using 3 as a cardinal number to reference a quantity. And if you want to scroll back up to the beginning of the notes here, when we made the distinction between number and numeral, okay, in number we're talking about cardinal numbers, because we're talking about the quantity, okay, right here. In numerals, we are talking about the symbols, the symbolic representation. So it's important that you tie those concepts together, okay? All right, that being said, once you can have established and you've taught these concepts to your students, then you're ready to teach them more than or less than, which is what we call topic 2 here, ordering whole numbers, meaning comparing them, which in essence is what we do when we come up with more than, less than, or equal to. We are comparing 2 quantities and determining which quantity is more, which quantity is less, or are both quantities equal to one another, okay? So a little symbol that I want to draw your attention to, if you'll notice over here, we have the N and then paren, uppercase A, close paren. This symbol here, or this notation, means the number of elements in a particular set. So if we look at the definition of ordering numbers, we're going to go right here, ordering whole numbers. That is defined, the process of ordering whole numbers is defined where lowercase a, or the element, that's the element, okay, where lowercase a is equal to the number of elements in set A, and lowercase b is equal to the number of elements in set B. And if the following is true, wherein the number of elements in set A is less than or equal to B, or if the following is true, where the number of elements in set B is greater than or equal to A, then we can say that set A is equivalent, or that it is equivalent to a proper subset. And remember, this is a symbol that we use for a proper subset of B. What are they saying? Here's what they're saying, okay? Here we have set A, and here we have set B, okay? The number of elements of set A, remember we're using that lowercase notation now. So if A represents the number of elements in set A, then A is equal to 2 because there are 2 elements in set A, right? And if B represents the number of elements in set B, then B is equal to 5 because there are 5 elements in set B. Now, using our one-to-one correspondence, you see that we can only correspond the 2 elements in set A to the 2 elements in set B, and then set B has all these elements left over. When this is the case, when the number of elements in set A is less than the number of elements in set B, we can say that 2 is less than 5, and that is what we've done right here. Okay, and vice versa, the same is true if we were to switch the order. And it turned out that now, instead of this being set A, we called this set B. This was set B. And instead of this being set B, we call this set A, right? Then we would say that, and let me see if I can erase this to make it a little easier. Okay, so then instead of writing these things here, we would say that B is equal to the number of elements in set B, and that lowercase b is equal to 2. And then over here, we would say that A is equal to the number of elements in set A, and A is equal to 5. And if that's the case, then because A has 5 elements and 2 is less than, let me slide that up a little bit. And then we would say that because 2 is less than 5, then B is a proper subset of A. So you realize we have to always read from left to right. Now, I just wanted to show you the opposite example, but let's go back and look at the one that I wrote here and make sure that that's nice and clear for you, okay? So the example that you're seeing here, and I'm repeating it, I know I'm repeating myself, but I just want to make sure that I'm not confusing anyone out there, okay? If this is set A, and this is set B, and A, right here, A equals the number of elements in set A. The number of elements in set A is 2, so lowercase a equals 2. And B, lowercase b, equals the number of elements in set B. And we look here, and the number of elements in set B is 5, so lowercase b is equal to 5. Then we see that 2 is less than 5, right? Because we've used one-to-one correspondence, and we notice that B has all these extra elements. And therefore, that means that A, because 2 is less than 5, it means that A is a proper subset of B. That's what the definition up here was saying, okay? But basically, that just means that whatever is less than is a proper subset of whatever is greater than, okay? In simple language. Now, basically, in these notes or in this portion of the lecture, we've covered 3 methods that children are taught basically to understand numbers. We've talked about the counting chant, okay? And that we discussed in the introduction. Basically, children are taught to count 1, 2, 3, 4, 5. And because 2 comes before you get to 5, you tell them, well, 2 came first, so therefore 2 is less than 5, okay? But that doesn't always work because, as you saw from our examples, children learn the counting chant by rote. That doesn't mean that they have understanding of what's happening. So then another method that gets used is the number line, which is one that you're probably very familiar with, where we put the numbers on the number line and we say, well, 2 comes before 5 on the number line, so therefore 2 is less than 5. And this can be successful for many students. But the concept here of set theory, or the set method that we've just discussed, is the one that will help you the most when trying to help students understand why it is that 2 is less than 5. Again, it helps you the most in your understanding. I would never recommend you use this as a way of explaining it to young children. Okay? All right, there is homework that goes with these with this lecture, and it is already listed and dated on your tasks menu. I'm going to stop the share right now so that we can go back. There we go. All right, but the homework assignment is listed as follows. You're going to be doing numbers 1 through 6 on page 59, I believe. Apologies. I can't read that far away, and I don't get old, guys. Don't get old. Okay. But yes, I believe it is. Let me see if I can find it here. All right, so you're going to be doing numbers 1 through 6 on page 65. There you go. It's page 65, numbers 1 through 6. That's going to be your next homework assignment, homework number 3, I believe, or 4, homework number 4. And it should be listed on your task tab because you've already done homework number 1, which was section 1.1, homework number 2, which was section 2.1, part A, homework number 3, which was section 2.1, part B, and this is homework number 4 for section 2.2, part A. Page 65, numbers 1 through 6. It's already listed on your tasks tabs, and it will be due by 1 p.m. on Friday before our live session. We are still scheduled to have our live session on Friday at 1 p.m. like we did last week. The Zoom information is still listed under your content area on our Blackboard page for this course. Again, I'm going to be using it like I did last time as a way for us to be able to discuss and troubleshoot and give you any extra homework help that I can, or explanation of any concepts that may have gotten a little wonky for you just watching the video and reading the textbook. Okay, so I will see you on Friday. This is Wednesday's assignment, and it will be due on Friday before 1 p.m. before we have our live session. And then after our live session, you can access the information that will already be posted for Friday's class. Okay, take care, guys.